All right, hi chemistry students. This is a video on 10.4, rate laws and rate order. I'm actually going to split this video up into two because it's a lot of material. And so in this first video, we're just going to get an introduction into rate laws. And then we are going to be able to determine specifically the rate law and the rate order for a reaction once we have these basics. And so the question that I get class started with for this lesson is, which reaction will go faster, right? If we take a look at OH plus CH4 yields H2O plus CH3, and OH plus CH2Cl2 yields H2O plus CH2, which reaction will go faster? Now, on the surface, you'll see that they are quite similar in terms of reactions, right? One of them, we're reacting OH with methane, and the other one, we're reacting OH with a fluorinated carbon, CH2Cl2. Sorry, not fluorinated, chlorinated carbon, right? And so point is, they're very similar reactions. And so which one is going to go faster? On its surface, you might be saying, they're probably going to go the same speed, right? And or you might say, I don't know, man, I can't tell by just looking at reactions. And you're right. In fact, yeah, we don't know just by looking at reactions. And so, but yet chemists want to have a way of being able to describe which reaction goes fast and which goes slow. And not just to be able to say like, oh, this is fast and this is slow, right? But to be able to give it a number to quantify how fast and how slow. And so we do have a number for that. We have this thing that we call the K value. And it turns out that the K value for this one is K is equal to 7.7. And for this one, K is equal to 1.1. Now you might be saying, okay, that's great, but what the heck does that mean? Well, it turns out that the higher the K value, the faster the reaction. The smaller the K value, the slower the reaction. And so here, K is equal to 7.7. That's higher than 1.1. And so what we're going to say here is that this is going to go faster. Now, you can only tell that, though, because I gave you the K value, right? You can't just look at this and be like, oh, yeah, this is a fast reaction, this is a slow reaction, right? You need the K value. And so the K value is our way of determining and quantifying the speed of reaction. And so if K big, reaction fast. If K small, reaction slow. Now, the way that we use K and the way that we get K is by creating an overall equation for the rate of our reaction. So let's say we have the generic A becomes B, right? Some reactant becomes some product. The equation for that, the equation for the rate is going to be equal to K, what we call the specific rate constant. Sorry, let me just make sure I got that vocab right. We call K, the rate constant, and then that's going to be multiplied by the concentration of A. Now, you remember, right, that we said that concentration of A is, or concentration of our reactants is one of the things that determines speed, right, in 10.1 when we were talking about collision theory. And so we see it here. K actually is a combination of all the other factors, like the size of the particles as well as the temperature. And so in class, I derived that a little bit for you guys, but because this is just the basics, I'm not going to go into that, right? But so concentration of our reactants is going to be important. We're going to put it here. And then lastly, we have this A, it's an exponent, and so that's going to be rate order, which we're going to be able to determine in the next video. And so this is how generically you write the equation for rate for a reaction is basically equal to K times the concentration of our reactant to some power. And so that's generic, that's theoretical. Let's look at some specifics. And so let's say we had 8 Fe plus S8 yields 8 FeS. What's the rate law? We call it the rate law, not just the equation for rate. It's called rate law for some reason. What's the rate law for this reaction? Basically, the rate law is going to be equal to here. Rate is going to be equal to K times the concentration of Fe, and we'll say to the power of A, and then the concentration of S8 to the power of B. It's as simple as that. Now, if you go on and take more chemistry, you'll learn that I'm actually simplifying a little bit for you guys, but it's okay. This is just the basics, right? So K times the concentration of Fe to the power of A, and S8 to the concentration of, concentration of S8 to the power of B is your rate. Equation for rate. And so let's do this one too, right? Very simple. Rate is going to be equal to K times the concentration of Na3PO4 power of A times the concentration of KOH to the power of B. And that's it. All right, so rate laws are actually really easy. Writing rate laws, quite easy. Graphing this now is going to be a little bit more challenging, but still something that we can do, right? So let's say we have A goes to B, right? Our equation here is rate is equal to K times the concentration of A to the power of A. And the question then is, right, if we were to plot the concentration of A against time, right, what's that going to look like, right? We know that A overall is going to decrease over time, right, because we have something, and it's like, okay, well, it's going to decrease, but how is it going to decrease? Is it going to be like this, right, like that's our first option? Or is it going to be more of like, it decreases at a decreasing rate for my students who are taking calculus, right? Or is it going to be, is it going to increase very quickly at first, or sorry, not much at first, and then super quickly, right? So increasing or decreasing at an increasing rate, right? So option 1, 2, or 3, we don't know, and so, or at least we don't know yet, and so let's figure out how we'd actually graph it. And so it's actually going to depend upon the value of K as well as our initial concentration. And so say K is equal to 0.1 molarity per second. And we have 10 molarity of A. This A sub 0 means just A, the concentration of A at time 0, so A, the concentration of A at the beginning. And so let's say it's that. Now we're going to just assume, and we're going to kind of we're going to assume that A is equal to 1 here. And so again, we'll learn in the second half that that's actually not always true, but let's just say that for now. And so what we can do is we could graph this out and say, okay, well, at different times, what's the concentration of A going to be? And therefore, what is the rate going to be, right? And so at time 0, what is our concentration of A? Well, if R is equal to 0.1 times the concentration of A, which is 10, right? Basically, and remember we said A is going to be equal to 1, and so R is going to be equal to 1 molarity per second, right? And so at that time, now also, our concentration of A at time 0 is 10 molarity, right? That's what we said. And so we have a concentration of 10 molarity, and what's happening is the rate is it's going to be decreasing at a rate of 1 molarity per second, right? From plugging it into here, right? R is equal to K times, right, the concentration of A, which is 10, put it here to the power of 1. So it's negative 1 molarity per second. And so that's what we start off with. We're at time 0, and the concentration of A is 10 molarity, and the rate at which it's decreasing is 1 molarity per second. Now do note, then for time 1, what's going to happen basically is if this is decreasing at a rate of 1 molarity per second, right, what's going to happen after 1 second? Well, we're going to have lost 1 molarity, and so after 1 second, we're going to be at 9 molarity. Do you see, though, that that's going to result in, now our rate is going to change, because it's going to be 0.1 times 9, so it's going to be minus 0.9 molarity per second. And so at time 2, we're going to be 9 minus 0.9 molarity, and so we're going to be at 8.1 molarity. And then similarly, we are now going to be at 0.081 molarity per second, right? And what we see is that our rate is decreasing over time, and that makes sense, right? Because our concentration is decreasing over time, our rate is going to be decreasing, and thus, here, do you guys see what's happening? For my students who take calculus, this is very easy right now. You're like, yeah, I've seen this all the time. This is a very easy concept to me, but for those of us who haven't, basically what we're seeing is that we're decreasing, right? We're going to be using up A, but we're going to be using up less and less over time. And so we're decreasing at a decreasing rate. So what that looks like is this. In general, in general, decreasing at a decreasing rate means, hey, our concentration of A over time is going to be decreasing, it's going down, but over time it's going to be doing that more slowly, right? At the beginning, right, it's happening a lot. Oh no, we're losing a lot. But then over time it kind of balances out. It's like, okay, you're not losing actually that much each second, right? And so that's decreasing. It's still decreasing, right? We have a downward slope, right? It's decreasing. A is decreasing, but it's decreasing at a decreasing rate. It's not happening as quickly. And so this is generically what it's going to look like. And so what we can do is, if we get a couple more points, and I'll just put these in for us, right? You can double check me if you'd like, but right, and this is from oops, sorry. Again, double check me if you'd like, but I think you're getting the point. Right, this is what we're gonna get, and what we can do is we can plot this. We can plot this here. Concentration against time, and what we'll see is that, you know, if we start off here, 10, 9, 8, 7, 5, sorry, I need some more room. 5, 4, 3, 2, 1. And this is not my best graph. I should have used graph paper, but it's okay. Time 1, 2, 3, 4, 5, 6. Of course, this is in seconds, right? What we'll get is we start off, as we mentioned, at time 0 at 10, and so we can put that there. And then at time 1, we are at 9, and then at time 2, we are at 8.1, and then at time 3, we are at 7.29, and then at time 4, we are at 6.5, and of course, again, my wonderful graph isn't that great, but because I didn't put this on graph paper, right? But what you'll see is something like this if you actually put it on graph paper. And so I'm just going to cheat and put that up there. But again, please use graph paper. You'll see this much better. And so this is the concentration of A over time. We can see it's decreasing at a decreasing rate. Now, here's a related question to you, for you, right? Let's say, this is the rate of disappearance of B. What is the rate of appearance of A? Oh, I'm sorry, I totally messed that up. What is the rate of appearance of B? So this was A. What is the rate of appearance of B, right? As this goes away, what's happening to B? Well, think about stoichiometry, right? When we were making sandwiches, right? If you used up 2 pieces of bread, how many sandwiches did you make? You made 1 sandwich, right? They were in stoichiometric ratios. In essence, you know, how much bread you used was directly proportional. It was in ratio with the amount of sandwiches you made. Right? And so it is here. Basically, the amount of A we lose is going to be equal to the amount of B that we gain. And so what we can do is we can kind of plot this in a similar way. It's like, okay, after 1 second, how much B do we have? Well, after 1 second, if we lost 1 molarity of A, we're going to have gained 1 molarity of B. And how much are we going to have after 2 seconds? Well, if we have 8.1 molarity A, we'll have approximately 1.9 molarity B. And then how much after 3 seconds, right? After 3 seconds, we'll have approximately 2.7, right? And so what you'll see here is you should have also increasing at a decreasing rate, right? We're going to be increasing the amount of B, but that's going to slow over time. And so what we can see here is the stoichiometric ratio. And so this is kind of an interesting little thing. And overall, this is how you graph. And so hopefully this helps you guys out with the basics of graphing, the basics of rate laws. And so hopefully that helped. Let me know if you have any questions.